everyone. My name is Balu. I'm a final year PhD student at the University of Melbourne. I work with Professor Stuart White and Dr. Bradley Gregg. Final year means implies that I'm actually looking for a job at the end of this year. So if you have got money, do let me know. Yeah. So this is actually based on a paper which we submitted a few weeks ago, and I'll be talking to you about how we can constrain the astrophysics of the yearly galaxies in the yearly universe. Yeah, so we are looking at this epoch. So we have the formation of the first luminous sources in the universe. The first luminous source being the first galaxies and the first stars. They emit these intense UV and X-ray photons, which ionize the IgM. So what we do in our team is that we make large-scale cosmological simulations of this epoch. So there's a lot going on here. So the fiducial simulation is called a L2 org. Now that's a simulation which is actually based on the or on an augmented Genesis simulation box. So the main thing about this simulation is that it's actually have a statistically complete galaxy population, and the fiducial simulation is also calibrated with respect to the UV luminosity functions, same optical depth, and so on. On the top right-hand side here, I'm actually showing you the EOR morphology. So the golden yellow here is the H1 gas in the IgM, and the blue is the H2 regions. And at the bottom here, I'm showing you the brightness temperature from the simulation. So which is a proxy for the thermal state of the IgM. So here is the ionization state, and here is the thermal state of the IgM. As you can see, in the beginning, we don't have a lot of luminous sources, but as you have the formation of stars and galaxies, the gas actually becomes hotter and hotter, and at the end, it actually starts it actually starts going in the emission as well. So what we did in so what people like Nicole actually look for is that they actually look for signals from this epoch. So what they look for is that they look at the H1 emission across the whole sky, and they can actually take a mean of this emission in the sky, and that's a signal on the left-hand side here. Well, what you can actually, something else you can do is that you can actually subtract out this mean value, and then you can talk about the fluctuations of this emission across the sky as a function of scale. And that is the 21 centimeter power spectrum. And what we wanted to do in this work is that we wanted to look at what can we actually learn using this signal from the yearly universe. So for this one, I should also introduce our basic simulation model. So this is apparently a dark matter halo here, and you have the IgM, which actually cools down into the dark matter halo, which actually further cools down, and you have the formation of something we call a cold gas disk. And when the mass of this cold gas disk actually become larger and larger, you will have the formation of the first stars and so on inside the galaxy. So we have something called the alpha SF, which actually sets the star formation efficiency, and the sigma SF, which is the minimum mass you need so that this star formation actually starts in the first place. So after some time, you have a beautiful, nice galaxy here, and the stars age and they die, so they go supernova. So what a supernova actually does is that it actually heats the cold gas in the galaxy. So sometimes the cold gas actually becomes a hot gas, but still stays within the galaxy. But if the feedback is very strong, a portion of the cold gas will actually be stripped from the galaxy as well. And that's actually controlled by the eta and epsilon nodes. And the galaxies also emit a lot of photons. So we actually follow the X-rays as well. So the amount of X-rays in the IgM is actually set by the X-ray luminosity of the galaxies. And we also track the UV escape fraction of these galaxies. So for example, here the F escape 0 actually sets the amount of UV escape fraction. So moving on, yeah. So this work we wanted to look at what can you actually say about these parameters in our model if you actually observe the 21 centimeter PS. So since we're actually looking for a future observation, we can actually forecast this. That can actually be done by something called a Fisher matrix formalism, where you're actually looking at the derivative of your observable, which in this case is 21 centimeter PS. And the second important thing is that we also need to have an estimate on your noise. This is one of my favorite things about working on simulations, because you actually get to simulate your noise. And the reason why people care about this is that under some very strict assumptions, the covariance matrix is actually the inverse of the Fisher matrix. So when you do this exercise for the 21 centimeter PS, you get this plot here. So for this one, we are actually looking at 1,000 hours of observation with the SK1 law. And we are also looking at something called the moderate foreground scenario, where we are not including the K modes, which are actually dominated by the foreground noise. So the main output from this plot is this plot here, so where I'm actually showing you the percentage error on our model. And this dashed line here is basically the 10% line. So we see that there is a fairly tight constraints on the X-ray properties, while we only have moderate constraints on the UV escape fraction as well as the star formation efficiencies, for example. And we only have very weak constraints on the supernova feedback of the galaxies. So what you can actually do in this case is that you can now include more information in your analysis, which we do by including the UV luminosity functions. And yeah, so the main motivation for using UV luminosity function is that the UV luminosity function is actually very sensitive to the amount of stars in the galaxy, and the amount of stellar mass is actually very sensitive to the amount of star formation as well as supernova feedback. So when we do this, we get the Fisher matrix constraints for including all of this information. 2 minutes. Where was I? Yep. So the main points here you need to note in this one is that if you look at the blue squares, which are the constraints from only the 21 centimeter PS, and also the plus signs here, which are the constraints from the UV luminosity functions, we see that we actually have fairly good constraints on the X-ray ones from the 21 centimeter PS alone. While if you look at the supernova feedback, we need the input of the UV luminosity function. And if you look at the combined case of both of them together, we actually seem to be having fairly good constraints, and we seem to be getting, for 6 out of 8 of them, we seem to be getting something like 10% error on our model. And I will just leave it here in the summary.